I hope everyone's doing well. I'm Mr. Thank you for joining me for this video where we're looking here at Fischer Esterification procedure in an acid catalyzed environment. We are looking here at the generation of esters. Your basic reaction here is you're starting here with a carboxylic acid, and then in the presence of a alcohol we can generate an ester. We're looking here at an R group. Here's a different R group, and in acid catalyzed reactions we will have our ester develop. And it would look something like this. Here's your one R group, here's the other R group coming here from the alcohol as you see, and the elimination of water. What are your starting reactants? It's your carboxylic acid, your proton environment, and your alcohol. Your end results are the ester and the elimination of water. This right here is Fischer Esterification. We will be looking here at a good example, and we'll look at the 3 steps which are involved and the mechanism behind those steps. This is not difficult, it's actually rather fun. In the first step, we will look here at the protonation of the carboxy group. What is our starting reactant here? We will start here with acetic acid, CH3, C double bond, OH. Your carbonyl group, oxygen here, can behave as a Lewis base. You have a proton which is floating around in the environment. This can attack that and generate a oxygen-hydrogen bond by using 2 of the electrons of the 4 total on that oxygen. When you do it, you will develop a protonated carboxy group, and it will be charge deficient, and I'll talk why. This right here is a natural state of oxygen, 4 lone electrons. When you've used 2 of those electrons, some of them being shared by hydrogen, the oxygen is naturally charge deficient, so you represent it with a positive charge. This here is your protonated carboxy group, and it's able to form even though it's unstable. But why is this reaction likely to occur in this direction in the presence of acid? Because it can be stabilized by resonance. The fact that you can stabilize this by resonance by multiple structures will allow it to form, because you can discharge across the molecule to different parts. And I'll show you, here's another resonance structure as it can form. You can have a shuffling of electrons such that now you can bring the positive charge by returning 2 electrons from the duplex of this carbonyl. The double bond, I've broken 1 and I've returned 2 electrons, and the positive has ended up on the carbon, and we have this. As you can see, you have this oxygen with 4 electrons, and you can now shuffle electrons again. And then when you do so, what you have done over here is demonstrate a double bond now with the other oxygen, and it looks something like this. And here is our original carbonyl oxygen, which is a hydroxyl group. These are your resonance structures which stabilizes what you see over here, and it would look like that. This right here is what we're looking for at the end of step 1, protonated carboxy group. But I'm just showing you can stabilize it by resonance structures, and so the likelihood of it forming is good. Our step 1 ends here with the protonated carboxy group. Step 2 will begin from that. Step 2, we do an attack by alcohol. What will my alcohol be? It will be methanol, CH3OH, and it looks something like that, CH3OH. Here's my protonated carboxy group, my acetic acid with the protonated carboxy group. This right here, carbonyl carbon, is normally a good site for nucleophilic attack because it's charge deficient. This is charge excess because of a dipole in the direction of oxygen. Right over here you can do a nucleophilic attack, and our nucleophile will be this, methanol. You can bring in the methanol, CH3OH, and you will attack it right over here. When you attack it over here, you'll have a shuffling of electrons, and I'll show you the next end result, which will be this. You have CH3 over here, you have C, you have a O and H. The 2 electrons have been returned back to the oxygen, the charge deficiency is gone, but now I'm focusing over here with the alcohol attached, and I have OH over here. This OH is from your original acetic acid, your original carboxylic group. And this is where I'm focusing on. You have 4 electrons here, but 2 of these electrons have generated an oxygen-carbon bond. Because oxygen is having to share those 2 electrons, you have a charge deficiency. This is what it looks like. What can we do from here? What we can do over here is fulfill this charge deficiency by breaking the oxygen-hydrogen bond. Because each single bond represents 2 electrons, we can take these electrons and return them back to oxygen. This can drift away as a proton. When you do that, what happens? Look, CH3, you have your C, you have this hydroxyl, you have that hydroxyl, you have this hydrogen going away, and then you have your OCH3. This OCH3 is coming from your alcohol right over here, CH3OH. The hydrogen has drifted away, as you see over here. Now we've developed a most important item in the entire procedure. It's a tetrahedral intermediate. It's a long-lasting species, but it's tetrahedral because it can go forward to the product completion, the ester, or it can go back to your original reactants. This right here is the most crucial step. It can go either in the forward or the reverse direction based on your reaction conditions. But at the end of step 2, we've generated this tetrahedral compound, CH3COH, OH, OCH3. Now our step 3 will continue from that. Tetrahedral compound, tetrahedral intermediate is more of an intermediate, you can call it that. The step 3 will be the elimination of water. When you're looking over here, look at it again. You have CH3, you have C. This part right here, or here, OH, this here, and that OH is coming from your original carboxylic acid. This OCH3 is coming here from your alcohol. It's all disguised, but this right here is your original carboxylic acid protonated and then shuffled around. This here is your acid with the elimination of a proton. That's what you're looking at. But from this molecule here, water has to come out to give you your end result, ester. How will it come out? You're looking here at this OH and it looks something like this. You have here a certain proton which is walking around in the solution. This oxygen can attack that. When it attacks it, you'll have here a protonated hydroxyl group, and it would look something like this. Here's your hydrogen, here's your hydrogen. This hydrogen is added and you have a positive charge. You've lost 2 electrons to gel up this oxygen hydrogen bond, hence oxygen is charge deficient because it's partly lost an electron to hydrogen. You have the OCH3 over here. This has to drift away to give you your elimination of the water. But let me redraw this over here. You have a OH here on the top which looks something like this. 2 of these electrons are going to come down to develop a double bond between carbon and oxygen to make that carbonyl. This water molecule will drift away. When it does so, this is what you have. You have CH3, you'll have a protonated carboxy group again, and it looks something like this because you still have the hydrogen attached to the oxygen, but you've developed here your carbonyl group. As you can see, the water molecule right over here has drifted away, and now I'll just write plus H2O, it's drifted away. That's our elimination of water. Then you'll have this OCH3. And we are right over here at a protonated carboxy ester. This will now eliminate that hydrogen to give you your end result. And how will it go away? This oxygen-hydrogen bond will break, return the 2 electrons back to the carbonyl. The hydrogen will go away, and your end result will be your ester, CH3, C double bond O, OCH3, and that hydrogen going away as that. This right here is going to be methyl acetate, and that's how you call it. You have a methyl group, and you have your CH3C double bond O. This right here will be your ester because you have your CH3C double bond and then you have your OCH3. You can call this methyl acetate. It's another name for it, but it is an ester. Methyl acetate or methyl acetic ester. Either of those names is fine. Let's focus right over here. How did this hydrogen just pluck away, or how do these hydrogens just pluck away and return back electrons to oxygen? Well, what we can do is erase some of this because you've seen the mechanism, and I'll show you how that happens. You're looking here at a certain carbonyl oxygen which is protonated, and it looks something like this. And how does this hydrogen just pluck away? Well, you're looking here at a certain water molecule in that reaction mixture, or you're looking here at a certain alcohol molecule in that reaction mixture. Either way, you're looking at something which can behave as a Lewis base, or which is slightly basic compared to what you have over here. Anyhow, you can take these 2 electrons, they can hit that hydrogen and return the electrons back, and then this carbonyl oxygen is fully satisfied in terms of its original 4 electrons. This hydrogen goes back, and you've developed here a protonated water molecule which you know to be hydronium ion, or you developed a protonated alcohol which you know to be something like this. And this would be likely scenario. Why? Because your reaction is already acidic. You think most of the cations in your reaction mixture are really protons. These are such short-acting species they barely even last. Most of your reaction species will be protonated water molecules or alcohols. What you really have are hydronium ions, H3O pluses, and that's how the hydronium will form, because your water molecule will suck a hydrogen from a protonated carboxy group to regenerate your hydronium, regenerate your acid. You can also find alcohols too because they'll be protonated because of the same effect. Anyhow, we've seen the esterification procedure, step 1, step 2, step 3, protonation of the carboxy group, development of the tetrahedral intermediate by the attack of the alcohol and the elimination of water to give you your ester, and here it is, our ester and the water molecule which has been eliminated. As I showed you the elimination of the water molecule earlier on, and we erased it, but the water molecule indeed is eliminated. Thank you for watching.